Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. I'm Naresh Imani. I'm a faculty member in the Department of Electrical Engineering at IIT Hyderabad. So, this is week 6 of the course. In the last 5 weeks, we have seen the basic material properties and we looked at how the metals react when you have incident light. And then we also looked at what happens when you have light incident on periodic dielectric structures. That was photonic crystals. So in this week, we will focus on what are known as metamaterials and metasurfaces. There has been a lot of excitement in the space of metamaterials in the last 20-22 years. The reason is metamaterials are these artificial materials that have been created and there is no existing natural analog. So to understand what metamaterials are, let's look at this epsilon and mu quadrant. Okay, so on the x-axis I'll have epsilon, and then on the y-axis I'll have mu. So if you look at the various materials that we have seen, epsilon can range from negative to positive. Okay, for the moment, let's see that, let's consider that we are considering at a particular frequency. Okay, so if you have dielectrics, epsilon is positive. If you have metals, we saw that the epsilon can be negative, and it could even be doped semiconductors. The epsilon is negative. On the other hand, we have also materials which can exhibit a magnetic response. So that I'm plotting it on the y-axis, mu. So far what we have done is we have considered mu to be equal to 1 or mu naught. And we have justified that by saying that the magnetic magnetic response of the materials is not strong at visible frequencies, and hence we can neglect it. That was the justification we have made. But it turns out that it's possible to actually create some magnetic effects, and we'll consider that later in this lecture. All right. So the first part is we have metals, the dielectrics, which come in the first quadrant of this epsilon mu. So wherein you have both mu and epsilon positive, and then you have materials which have negative response, which is negative epsilon, which are metals and doped semiconductors. And you could also have what can be termed as a magnetic plasma, wherein the epsilon is positive and mu is negative, but this will occur in some magnetic materials like iron ore or cobalt and so on. So some materials which exhibit magnetic response. But mind you, this occurs only at RF frequencies. Okay, and the last quadrant is this the third quadrant, where both epsilon and mu are negative, and this is what we are going to consider in this lecture. So, and as I said, there are no naturally analogous materials for this. So all the materials naturally occurring materials will fall into these three quadrants, whereas this is this artificially engineered materials, which we will call as metamaterials. And to understand a little bit more about it, let's look at what happens in a regular material. Okay, so if you consider, let's say, a plane wave which is incident on a material, let's say I'll give my plane wave as E naught and exponential, and actually we'll write it in the general form. So I'll say that exponential k dot r, so it can be 3 dimensions, right? This is my plane wave. And if such a plane wave is incident on the material, what happens? Well, we'll have to solve Maxwell's equations. So I won't go through the algebra, but I'll simply state that if you substitute this plane wave, into, let's say, the Ampere's law, curl of E equal to minus dou b by dou t, right? If you substitute it and do some little bit of vector algebra, you'll end up with an equation of this form, k cross E. So wherever you had curl of E, it essentially becomes k cross E, and other side was dou b by dou t. So b is mu h. So, and there's a minus and there's a time derivative, and there will be a I term which cancels out, and you'll end up with omega mu h. Okay, dou b by dou t will be of this form. So you have to do a little bit of algebra to get here. Similarly, if you take the curl for the magnetic field and substitute, let's say, the magnetic field expression for plane wave, you will end up getting k cross h equal to, in this case the other side was dou d by dou t. Okay, there is a positive sign, so minus I omega t. So minus epsilon mu e. This is what you will get. Okay, you'll have to do a bit of algebra to get here. So now what I want to do is let me write the magnetic field in terms of electric field. So I'll say H equal to K cross E by mu omega. Okay. What we're interested in looking at is the Poynting vector. You might have studied about Poynting vector, which is represented as S, and I'll say it is half of real part of E cross H. Okay. So now if you have a material, regular material, what is the Poynting vector? You might have heard that, okay, Poynting vector represents the direction of energy propagation. Okay. So what is it? So if I want to find out what is E cross H, what I can do is substitute E cross H. So basically I'll just E cross H is going to be E cross, let's say K cross E divided by mu omega. Okay. And E cross K cross E is essentially, you have a vector identity, A cross B cross C will turn out to be A dot C minus, I think it is A dot B times C. Okay. So if you do that, what you'll end up getting is E square divided by mu epsilon K. Okay. A dot B times vectors, A dot C times vector B. So that will be this. So E cross H equal to E square by mu omega K. Okay. What this is telling us is the direction, the Poynting vector is in the direction of the K vector for a regular material. That's what we have shown here. So if you consider the electric field and the magnetic field, we said that the wave vector is always, perpendicular. We said E cross H, they form a triad, essentially the right hand triad. If I take my right hand and do an E cross H, essentially that's my K direction. So or you can look at it in terms of fingers and so on, the right hand thumb rule. So you get this, and the Poynting vector also is along the wave vector. Okay. But if you have a negative index material, if you look at here, now in this case something unique happens, where if you have both epsilon and mu negative, quickly if you go back into this equation, let's say you put epsilon equal to negative and mu equal to negative, you'll see that H and K follow left hand rule. The regular material, it is a right hand rule where you put E and K along the fingers, and then the thumb points to the direction of K. Whereas for left-handed materials, you'll see that E, H and K follow the left hand rule, and that's why these materials are also called as left-handed media. And essentially what happens in this case is the S is in the opposite direction to K. Okay. So that's what we are saying. You put mu negative here, S is opposite to K. And similarly, I can start with, let's say, the electric field and then do an E cross H, and then you'll still see the same thing will obey even if you have mu. So the other equation that you will get is in terms of H, you could also show that this is equal to H square divided by epsilon omega K. Okay, you'll be able to show this. So basically, when both epsilon and mu are negative, this E, H and K form negative, follow left hand rule, and S is opposite to K. Now this is something very, very significant, because we are actually seeing that the fundamental way in which the electromagnetic energy propagates is changed, and that has tremendous implications. And that is why at the turn of the century there was a lot of excitement around these negative index materials. Okay, now what are these negative index materials? Well, we have seen resonances, right? I mean, we initially talked about the Lorentz oscillator model when we are talking about the optical properties of materials, and we have also seen what happens when you have let's say a resonance, plasmonic resonance, or even a me resonance, in a dielectric nanoparticle. They obey what is known as a Lorentz oscillator. So I can represent my epsilon, real and imaginary parts, again in terms of Lorentz oscillator, and we'll see that whenever the resonance happens, the epsilon or mu can actually become negative. We have not shown you any examples of how mu can be negative. So far we have considered mu equal to 1, but in this week's lectures, we'll actually consider how can we get magnetic response, or how can we get magnetic permeability mu to be not 1, but show something like this form. How do we get that? Okay, we'll consider that this week. But epsilon anyway we have seen it's plausible. So, and I've already shown this slide once in I think the first or second week, wherein we talked about this, and then we said I can represent that epsilon and mu in the complex plane in this fashion. So I can in the real axis I can have one of these. Real axis is x-axis is my real part of epsilon or mu, y-axis is my imaginary part, and then I can show, let's say for example I'm considering mu. Okay, initially if I discussed this in the first week, when there is no magnetic response, there's no imaginary part, it's purely real and it's 1, and then there is this epsilon which can vary over a certain along a certain angle. It forms a vector in this complex plane, and then your n is essentially, Maxwell's equations tell us that n square is epsilon times mu, so n equal to root of epsilon mu. And so if you have such materials which exhibit a magnetic response, then it is possible to create a negative index material. That's what I mentioned. Okay, and we have seen that. If not, you just go back and refer to my introduction in the first or second week. I'm not certain where. All right, this slide would appear there. Okay, so you can get this magnetic response, but how does it form an index? It's just one Lorentz oscillator. The example that we have shown so far is only one resonator, right? Let's say surface plasmon, localized surface plasmon in a nanoparticle or such. But how do we get a material out of it? And the idea here is this. So you take these individual elements which are exhibiting magnetic and electric responses, and then arrange them in a periodic fashion. Just like a regular material, wherein you can actually have response which is coming because of these individual atoms. So the electrons are confined to this lattice site, and then periodic arrangement of it will give you all the properties. Similarly, I can have a meta atom. So this particular unit here, let's say 1 unit of this, I'll call it as a meta atom. This could also be this, right? You can have various types of meta atoms, that is one individual unit cell in this, and then you systematically arrange it in some 3 dimensions and you get a material out of it. And that is what is known as metamaterial. In this, the word metamaterial is the meta word is derived from Greek, which means beyond the naturally occurring material. So it is a metamaterial. And there are various geometries that people have investigated over the last 20 years, and some examples are shown here. On the left, on the top, you see here, this is a metamaterial which is consisting of what are known as split ring resonators. So, okay, let me label this as 1 here, and this is split ring resonators. So I'll describe in more detail what is a split ring resonator later on. But it turns out that these split ring resonators can give you negative index in RF frequencies. So this was the first demonstration of a negative index material. This was out of Professor David Smith's group at Duke, and at that time he was not probably at Duke, but anyway, it was from Professor David Smith's group, and it exhibits a negative index at 10.5 gigahertz. Now there is also interest in trying to push it to visible frequencies, and this a lot of interesting work has been done in Professor Shalaev's group at Purdue, and 2 examples are shown on the right here. So these are again meta atoms. Now the meta atom is consisting of paired nanorods. On the top you see 2 nanorods, metallic nanorods, which are at a certain distance, and if you take that as a unit cell and then repeat it in 2 dimensions, you get a metamaterial again. Okay, ideally we should make it in 3 dimensions, but it becomes challenging to do it in optical frequencies. So yeah, what you're showing here is a plane of containing this paired nanorods. And the third example is this on the bottom, which is known as a fishnet structure, which is also again demonstrated in Professor Shalaev's group. So this also exhibits negative index. Okay, and the fact that you might say, so what? I mean, what are the implications? It turns out that if you have a negative index, there are a lot of counterintuitive things that can be observed. One of the famous examples you see is this, this picture you might have seen. So if you take a straw and put it in a glass containing water, you will see, just if you observe closely at the interface, it feels like the straw has actually a jump. Okay, and this is nothing but Snell's law. Okay, that the straw bend. This is something you can do at home and check. Put a straw in a glass beaker and you'll see that there is a jump around the interface. Okay, but the moment, let's say, imagine that there is a medium with negative index. Okay, so this could be water, just water. water has an index of n equal to 1.33. Suppose I do this experiment with, let's say, negative index. Instead of this, I'll say n equal to minus 1.33. This is, this is a thought experiment right now. This is not real, okay? So if it was there, what would happen? The straw, instead of bending in this fashion, it will bend in the opposite direction. And that gives us a lot of flexibility in designing electromagnetic materials. Now, for example, think of, let's say, radar, right? I mean, if you have an aircraft flying, you are essentially detecting an aircraft using radar. You are sending an electromagnetic wave and looking at its response and then the time delay and so on, and then we are determining where the flight is. But suppose if I want to shield the aircraft, I want to have, stealth. So if I am able to bend the beam that is incident on the plane at will, then I can nearly make my plane to be invisible to radar. Okay, so this occurs in gigahertz frequencies, right? The radar operates in gigahertz frequencies. So you can imagine if I'm adding a new dimension which has no existing natural analog, it opens up a lot of design flexibility, and that is the reason why there's this interest in negative index material. And a more maybe intuitive way of looking at it is this. If you have a positive index, this is my positive index with both epsilon and mu equal to greater than epsilon and mu both greater than 0, and so I can it obeys the natural Snell's law. So sorry, sin theta 1 equal to n2 sin theta 2. We have seen this already. So a light incident on this bends in this fashion. That there's nothing surprising about the figure on the left, but the figure on the right is a negative index medium, and now it exhibits a different behavior. So this is my negative index in the bottom, and then air is still there. There's an interface between the positive and negative index, and so you'll see that quickly. I mean, suppose if I take my n2 to be negative, what does Snell's law tell us? You can take my minus sign into the sign, and it tells you that the wave bends in the negative direction. So in effect, if you have a negative index medium, the refraction angle is negative. So when you have a regular medium, the wave is incident and then it goes to the other side of normal. That is by convention called positive angle. But if you have a negative index medium, it bends in the opposite direction. Okay, this is from Snell's law. It is, just considering that sine theta, minus of sine theta equal to sine of minus theta. But then you can also think about it from the momentum conservation arguments. So we have also shown that Snell's law can be derived from momentum conservation arguments, and it so happens that if you have a negative index medium, you can think of the wave vector here like this, and we also know that momentum has to be conserved at the interface. The tangential component is going to be continuous, and then the wave vector has to be opposite now, and so the only way that can happen is this way, and therefore your wave vector in the negative medium is like this here, and that's how only in this direction the wave can bend. So one of the boundary conditions arguments for arguing that the tangential component of the wave vector is conserved, we can show that the only way to have the wave to propagate in a negative index medium is if it bends this way. All right. So this might sound like just hand waving. So what I did was I just did a quick simulation, and my students did the simulation. So this is how this is what we can call as a simulation in it using a technique called finite difference time domain, wherein I'm showing a plane wave which is incident on the interface. So this part of it is basically, this is my interface between the positive and negative medium. So this is okay. I want to show you the positive index. So let's consider the case where, let's say there are two refractive index. This is an interface in the center here, and light is incident on that, and this is the plane wave fronts which are propagating. This is different from the COMSOL simulation I showed you earlier in the first week. This is the time domain picture. You can actually capture how the wave is propagating in time, and you will see that the wave has hit the interface and then it bends and then it propagates along that. The wave fronts are even closer. So you make all those observations. I'm actually making these videos available on the GitHub page. You can go back and look at it, and you'll see that the spacing between the wave fronts is larger. In the higher index medium, they're closer and it bends, right? This is how a wave will propagate in a positive index interface between two positive index media. But then if I have a case where it's actually you're having a negative index medium, the second part of it is a negative index, see what happens. The wave is incident as what you would expect, and then it hits the interface, and now it looks like something strange is happening, but just give it a moment, you'll see what's happening. Okay, the wave is now more or less going into the negative index medium. All right, so now you see as it propagates in the negative index medium, you will see that it appears as if the phase fronts are moving towards the interface. The energy is going to the right side of my screen, but the phase fronts seem to be moving in the opposite direction. So I'll just do it one more time just to observe. See, this is at the interface we have come, and then it's moving into the negative index medium. And in the negative index medium, the phase fronts are actually moving towards the interface, but the energy is propagating opposite direction. So that is what I meant when I said that the S and K are opposite in a negative index medium. Of course, this is a numerical simulation. We just try to put a negative index and create a negative index and just show this effect. But you get an idea of what is, what I'm talking about, the left-handed nature of a negative index medium. All right. So in addition to the intuitive arguments, this is something that actually can be verified. Okay. And if you are paying close attention, one of you might say, wait a minute, you said that n square, let me say, n square is equal to epsilon mu. Okay. That's what we said, we can derive from Maxwell's equations. And then I can simply put it as, that means n equal to root of epsilon mu. And if both epsilon and mu are negative, how is the index negative? Okay. It turns out that when you take this root, there are two terms. There are positive and negative root, and usually we end up taking always the positive root. Okay, that's what we have studied in the traditional physics, okay, or optics. But when we want to describe a negative, why should we take a negative root? I mean, just because epsilon and mu is negative, right? Why should I take the negative root? So we can understand that based on the principle of causality. So if we go back and look at, let's say, what we said was epsilon, I can take my epsilon, I'll write it as -1 plus I delta 1. Okay. So I'm just saying that the imaginary part is positive because we're assuming a passive material. Let's assume, because there's no gain in the material. So if I have a passive material, epsilon has to be of this form. Similarly, mu has to be of this form, I delta 2. Okay. Both epsilon and mu exhibit passive response. Okay, so we generated out of things like metals and things like that. There's no gain. Okay, so now if you do that, what happens to the resultant material? So let's try to take the root of this. Okay, so if I take a root of this, root of epsilon mu, I'll just simply write it in the expression here. So -1 plus I delta 1 into -1 plus I delta 2, and then the whole thing I'll take a root. Okay, I can expand, and then let's assume for a moment that delta 1 and delta 2 are small. Okay, assume delta 1 and delta 2 are small. I mean, basically we have small loss. If you have small loss, so this whole the square root of epsilon mu turns out to be +1, and then there is I delta 1 into I delta 2 will give you minus delta 1 delta 2, and then there is a minus I delta 1 plus delta 2. Okay. Right, this is what is going to be my root. So I can do a Taylor expansion, and let's ignore delta 1, delta 2. The product is much smaller because both delta 1 and delta 2 are small. So I should end up with 1 minus I delta 1 plus delta 2 by 2. Now the question is, what route should I choose? In principle, this can have both positive and negative. What should I choose? From causality arguments, if I am creating this metamaterial with negative index out of passive materials with both epsilon and mu having passive or positive imaginary part, then the resultant material has to have a positive root. Therefore, if you choose, let's say, a positive root if you choose, basically you have material with gain, whereas if I choose a negative root, material with loss or passive material, right? And so I can't create a material with gain out of passive material, so the first route is not possible. You will have to have a case where this is correct. Okay, so therefore, if you have both epsilon and mu negative, the only way to write refractive index is epsilon equal to minus root of epsilon mu if epsilon comma mu are less than 0. Okay, so this is a conclusion, right? Now we'll worry about, for the rest of this week, we will worry about how to create this both epsilon and mu negative. All right, and then I just want to point out one small thing, one comment before I close. That is, there are various length scales that are available for metamaterials of photonic crystals. The length scale is very, very important feature. What I mean by that is, let's say you have a periodic structure. Okay, I'll call my periodicity as A. Then the ratio of A and lambda becomes very, very important. Okay, so you can have a situation where A is much, much smaller than lambda. That means, just like in a regular medium, right? Wherein the let's say if I have glass, the periodicity of, let's say, the distance between the silicon and oxygen atoms is very, very small. Maybe few picometers, right? Compared to the wavelength, which is hundreds of nanometers. So it's very, very small. So effectively, you don't have to worry about the interatomic spacings, the forces and all that, simply represented by an effective index. Similarly, if your periodicity of the materials is much smaller than lambda, we can represent that such a material, be it this sort of a split ring resonators or a fishnet structure, out of using what is known as an effective medium description. Okay, and you can define these quantities epsilon mu, n and z. I mean z in this case, or z in this case is the impedance. All right, so you can do that. Whereas if your lambda is of the order of A, like what we have seen in the case of photonic crystals, the distances are much larger. The periodicities are comparable to the wavelength. When you have periodicities comparable to the wavelength, then actually we have to worry about the diffraction and interference effects, and then we'll have to look at the band structures and so on. And this we have done in the photonic crystal examples. Okay, so we'll have to understand. So this is photonic crystals when the scale is of the wavelength, of the order of wavelength, and if your size of the minimum distance is much, much greater than lambda. Let's say I'll consider a glass ball, let's say, which is much, much larger than 500 nanometers light. Then I'll have to look at reflection, refraction, and so on. The traditional geometrical optics works, okay, in this regime. So this is the traditional geometric optics. This is a photonic crystal regime where we have to worry about the interference and diffraction and so on. We can calculate band structures, we can analyze this. And if you have A to be much, much smaller than lambda, then we can look at metamaterials, okay, or even natural crystals are similar to this. Okay, so you can have this scenario. So the quest of the metamaterial community in the last 20 years has been this. So there's a lot of activity till up to, I think, 2010-11, okay, in trying to create these metamaterials with effective medium description. All right, so we will do that. Okay, so we'll consider more about it in the coming lectures. So with that, I will stop here, and in the next lecture I'll continue. Thank you so much for your attention. Take care. Bye.